Hello everyone, welcome to my presentation. I am Imrus Salehin and today I present a research paper, and this research paper is proceeding of the 34 International Conference of Machine Learning in Sydney, Australia. And the paper title is the Model-Agnostic Learning Meta Learning for Fast Adaptation of Deep Networks, and the research paper write the C. Finn, Peter Abel, and Sergey Levin. And now I represent the full paper with several contents like the introduction, motivation, model setup, algorithm analysis, result analysis, and the conclusion of and future work. So first of all, the introduction. In goal of the meta learning is train a model on the varieties of the learning tasks, such that it can solve a new learning task using only the small number of training sample. In meta learning, the goal of the trained model is quickly learn a new task from the small amount of new data, and the model is training with the model learn be able to learn the large number of different tasks. In this paper, the author focus on some major algorithm developed, like a meta-learning algorithm that is general and the model-agnostic. It can be directly applied on the learning problem and model, and the model is applicable to the various of the different learning problems, including the classification, regression, and the reinforcement learning. And the next is the motivation, why the paper introduce and why they work in this paper. Basically, the main things of this work is the meta learning is to train a model on the varieties of the learning tasks, such that it can be solved the new learning task using only a small number of training sample. And in meta learning, the goal of the trained model is quickly learn a new tasks from the small amount of data, and finally the model is trained by the meta learn to be able to learn on the large number of different tasks. So basically, here is the motivation section, and then we see the problem setup and which type of problem they solve in this paper. So basically, they create a problem setup in this paper, and in this section they formalize the meta learning problem setup in the general manner, including the brief example of the different learning benefits. And here we see here we see the equation. Here is the equation, and this is basically represent of this problem setup. And here we see a diagram. Basically, this diagram is a model agnostic meta learning algorithm. Which is the short form is MAML, who is optimized for the representation of theta, can be quickly adapt a new task. So we see here is the theta, and here is the bold line is the actually the meta learning, and here is the learning adaptation, which we see in the theta 1, theta 2, and the theta 3. And formally, the easy task consider of the loss function of L. We see here the loss function of L. Here we see the loss function of L, and the previous task is specific feedback, which is might be the form of the misclassification loss or the cost function in the Markov decision process. And here is the T, basically the task of P of tau, and they want to develop the model to able adapt of learning of new tasks of T, and drawn from the P of tau from the K of sample, and drawn from the Q, and the feedback of this feedback from the corresponding loss function of L of T from the T of I. Basically, this noted function we see in the next algorithm process. So basically, here is the ultimate problem setup, and basically the goal of the few short meta learning is trained to model that quickly adapt. So to accompany this, the model or the learning trained during the meta learning phase on the set of the task, and that trained model can quickly adopt the new task only the small number of example. So basically here is the problem setup. Then we see the algorithm section, and here is the algorithm section. There use almost 3 to 4 algorithm to complete this model. And first of all, we see the Model-Agnostic meta learning algorithm. They have proposed the model that can learn the parameters in any standard model via meta learning, such the ways of pairs of model of the adaptation. And first of all, we see the whole procedure of the algorithm. Here is the whole procedure, and first the required is P of T. This is the drawn of the new task without the overfitting and the distribution of the overtask. Then here is the alpha and the beta, the steps of the hyperparameter, and the randomly minimize the theta. And basically here they consider the model representation by the parameterized function of the f naught, f theta, and with the representation parameter of the theta. And the model parameters theta become theta dash in this method. They update basically theta to theta dash. We see here the theta dash from the theta, and basically they use the gradient descent. The model parameterized are the trained by optimized by performance of f theta dash with the respect of the theta and across tasks simply from the p of t. And we see here is the basic function, and the meta optimization across the task of performance via stochastic gradient descent, which is known as the SGD, stochastic gradient descent. And we see the update of the ending process. Here we see the SGD. So the MAML meta gradient update involves a gradient through a gradient, and computationally the requires additionally backward pass through the f of the computer Hessian vector product, and which is the supported by the standard deep learning barriers such the TensorFlow. And in this experiment they include a comparison of the dropping of backward pass and using the first order approximation. And the next we see the species of mammal, and in this section they discuss the specific instruction of the meta learning algorithm for supervised learning and the reinforcement learning. And we see the supervised regression and the classification algorithm whole procedure. And first of all we see the distribution task, and here the alpha and beta is the step size of hyperparameter, and there is the theta is the randomly initialized theta. And then the T of I, and the task of T of I generated by K of the observation X from the Q of I, and the task logs representation by the error between the model of output by the model of output of X, and the corresponding target value is Y is the observation task of the observation and the task. And the two common loss function use the supervised classification. Here is the regression and the cross entropy mean the square errors, the MSE which is described with a equation. And here in the k short regression task, k input and output pairs as the provide of the learning of each task. So we see here the update section. Here we see the update section, and here is the equation like the equation, if we write the equation, we see the L of t of I and the f of theta, and here is the period of f theta and x of j, x to the power j minus the y to the power j, and the matrix value is 2.2. So basically here is the equation where the x to the power j and y to the power j is the input and output pair sample task from the t of I. So basically here is the algorithm, the supervised regression and the classification. And the last we see the reinforcement learning. In reinforcement learning, the goal of the few short meta learning to able the agent of quick acquire and the policy of the new task, the using only the small amount of experience in the test setting. So we see here is another full algorithm development which is used in the reinforcement learning. First, they same as work in the previous, and they initialize the alpha and beta, and they randomly initialize the theta. And then we see here the simple k transaction which is denoted by d, and x is the input, a is the output, and x is using for the f theta. And in the t of I, this process basically here the RL task t of I contains a initial state of distribution of q of I, and the x of t plus 1 divided by x of t into at. And the loss in this task is therefore the Markov decision process with the horizon h. So here we see the ultimately the loss task of t of I, and the model of f theta takes the form of the equation, and the k short reinforcement learning is k roll out from the f of theta and the task t of I, which is we see here the simple trajectory of d of I is here the equation, and the last update is here is the here is the last update, and they detail the algorithm and they use the policy gradient method to estimate the gradient both from the model gradient update and the meta optimization. So here is the reinforcement learning algorithm. Then we see the result and analysis part. Actually, the goal of the experimental evaluation is answer the following questions, like can the mammal enable to learn a new task, and can the mammal use the meta learning, multiple difference domain including the supervised regression, classification and reinforcement learning, and the last question is can the model learn with the mammal, continue the improve the additional gradient update. So all the meta learning problem that they consider requires some amount of adaptation to new tasks and the test time. When the possible, they compare their result in the oracle and receive the identified task, and basically they use some famous algorithm to compare their task. We see in the next slide basically. So here is the next slide. First of the regression of the experimental result, we see here is the curve. There are the standard sample regression problem that illustrate the basic principles of mammal, and each task involve the regression from the input and output since the web of the Censored are the varieties between the tasks. We see the mammal of k of equals to 5, k equals to 10. Basically, we can see the graph p of t here is the continuous where the amplitude varies within 0.1 to 0.1 to 5. And the regression is the neural network model with the two hidden layer of the size of 40 with the ReLU non-linearity, and in the training with mammal using the gradient update. So we see here the three types of curve, and the step size basically 0.1, and is k equals to 10, and the step size is 0.2. And here we see the another graph. The another side, they have evaluated the performance by the fine tuning the model learned by the mammal, and the parameterized model which is the k equals to 5, 10 and 20. And in this curve showing the quantitative sigmoid regression result showing the learning curve at meta test time. And this improvement suggests that mammal optimize the parameters such that they lie a region that it enable to fast adaptation, and it's sensitive to the loss function from the p of t, and the overfitting perception that only improve after the solving. So here is the regression analysis curve, and then we see the classification result, and we see the table which is compared with the other algorithm to evaluate the mammal. The comparison of pure meta learning, basically we see the different types of algorithm, different type of algorithm with the using the new algorithm, the mammal and mammal. So we can see the all the result are decreased than the new algorithm, like the mammal algorithm. Here the 98.7, the others is less than this result, and another is the 89.7 which is the less than this another. And we see here is used basically the famous algorithm, and the dataset consists of the 20 intents of the 1623 characters from the 50 different alphabets. So to test the flexibility of the mammal, they also provide result for the non-convolution network. And then we see the reinforcement learning task to evaluate the mammal of the reinforcement learning problem. They have construct several sets of tasks based off the simulate continuous evolution. So we see here is basically the reinforcement learning result of the half character, the localization task with the task shown on the right from the right, and each gradient steps receive the additional sample from the environment, unlike the supervised learning task. And the results show the mammal can adapt to new goal factorize, and denoted the substantive faster than the convolution pre-trained on the random initialization, achieving a good performance in just 2 or 3 gradient steps. Finally, the method mainly proceed to where the initialization adaptation can be performed with any amount of data with the number of the gradient step. So the result we compare the 3 baseline model, basically the pre-train on the policy of the task and the fine-tuning, training a policy from the randomly initialized weight, and the oracle policy which receive the parameter of the task of input and which of the task below the corresponded goal and position and goal decision or the goal victory of the agent. And here also in reinforcement learning they use the 2D navigation. In the first meta RL experiment, they have studied a set of tasks where the point agent must be moved on the different position of 2D. So randomly choose of each task within the unit square. And the another part is the locomotion, and to study how well the mammal can scale the micro complex deep RL problem. They also study adaptation of the high dimensional locomotion task in the microscope simulator. So basically here is the result analysis part, and then we see the conclusion and future work. Basically they have introduced the meta learning method based on the learning easily adaptable model parameter through the gradient descent, and this approach has a number of benefits. And finally this method mainly produce a weight initialization adaptation can be performance with the amount of data and the number of gradient steps through we denoted that the state of the art result of the classification with only on the 5 example of per class. So here is the conclusion, and basically I think in the future it can be extended in the multitask initialization a standard in the gradient in the deep learning and the reinforcement learning. So that's all, and thank you for joining with us.